hold on. And the reason I say hold on is because those of you who've watched my other videos on the continuum hypothesis know or should know that that's not the end of the picture here. That you cannot take empty space and say, aha, well, it's an infinite number of infinitesimal points. It doesn't quite work like that. Remember your Cantor. You could take set U and then set each one of these infinitesimal points and have a one-to-one correspondence with, let's say, a counting number. 1 point, 2 point, 3 point, 4 point, 5 point, all the way up to Aleph Nought points. In other words, the lowest level of infinity that we understand that's, constructed, which would be the infinity of the rationals, the infinity of the counting numbers. But if you were to take each and every single one of those points and sort of mush them all together, you wouldn't have set U, now would you? Okay, because it would be like all the rational numbers between 0 and 1. That would not be the set of all numbers between 0 and 1. So you have to introduce the idea of the continuum here. You would have to go beyond simply what the reductionists would want to do, is break everything down into these discrete units. And to really understand set U, you would have to bring in the continuum, or the set, let's say the countability of the set of the real numbers, which will always transcend the countability of the set of the rational numbers. Okay, let's say I go back to the old 19th century brain. No quantum brain, no newfangled consciousness, new age, Kabbalistic mumbo jumbo. Let's go back to that good old fashioned meat and potatoes science. And I'm kidding when I say quantum physics, Kabbalistic mumbo jumbo. I'm ascribing a quote to the scientists who want to go back to the classical age. I have great respect for quantum physics and mystical understanding, but you know what I'm saying. Okay, and we're going to go back to that. In the 19th century mind, you have an infinite, let's say you have a thought, an infinite number of thoughts, and each thought corresponds to an individual mainnet, or an individual infinitesimal point. I know this one, I know this one, I know this one, and I have an infinite number of discrete ideas or thoughts about something. We can make it binary. It's going to be either 0 or 1 to make it simple. Okay, 0 or 1, 0 or 1, 0 or 1, 0 or 1. And if I know all the zeros and ones, I know the entire system. Now, you would argue that maybe it's multivariant. That's fine. But we'll just make it 0 and 1 for the sake of simplicity. We have a set U defined by 0 and 1. If you want to make it 0 through 10, that's fine. Make it 0 through 10. If you want to make it 0 through 100, I'm actually trying to make the reductionist argument even easier here by making it 0 and 1. Well, you know where I'm heading with this. Even knowing an infinite number of zeros and ones, you still don't know the entire set U, because you still don't know the continuum. And therefore, if I were to have an analytical mind that would attempt to know every single aspect of set U, in classical physics, I would still be limited by Aleph Nought. In other words, I would still have to have Aleph Nought numbers of 0 and 1s that I would have to know. And as you well know, once you bring the continuum into it, and you need the continuum for the entire set U, you would need not just, if I were to correspond it to a number line, I would need not just the rationals, but all the real numbers. Literally, to know the entire set U would be to go beyond anything I could know in my brain. It would not just be that I would need to have an infinite number of things I would know. It would not just be that I would need to have an infinite number of zeros and ones. I would literally, it would go beyond the infinite number of discrete thoughts or knowledge bits that I could have. Now, if I knew the continuum, now that would be kind of mystical there, okay, to know the continuum, in a sense, to go beyond the 0-1 binary limitations we would have. Well, that's another question altogether, but then you're going beyond the kind of analytical brain construct that the reductionists would really want to go with. If that's the case, maybe the question of determinism in classical physics would be decidable. But since that's not the case, and they would tend to shy away from something like that, I would say that the question of whether the universe is deterministic in classical physics is completely and totally undecidable. And with relativistic physics, the same thing. I mean, in the case of space and time curves, you still have a set U, you still have the same problem. Now, when you get to quantum physics, yeah, you can't break it down into an infinite number of infinitesimals anymore. You have Planck's radius. But then you have quantum indeterminacy you got to deal with. So you have a stripped on something there. So then you have you still have there. It's even harder to have a deterministic universe. Okay, so hence, in summation, I believe that even in classical physics, the question of whether the universe is deterministic or not is undecidable, and therefore I would say, if anything, it would not be, because a deterministic universe would seem to imply a universe defined by discrete bits, and I do not believe that it is, including the classical universe. Okay, last call here. I better hurry this up. I want any of you with any kind of information on the analytic-synthetic distinction to please write something in the comments section about some source I can go to, because I don't know a whole lot about it, to be honest with you. And the basics of the analytic-synthetic distinction would be, that goes back to Kant. The basics of the analytic-synthetic distinction would be for instance, if I were to make it, I'll give you examples to make this easy because I'm running low on time. If I were to say all bachelors are unmarried, that would be analytic, because I'm looking at the term bachelor in the plain meaning of it, not bachelor's degree or anything like that, but bachelor as in an unmarried man, and it's almost like a tautology. You know, the unmarried is implied in the definition. If I were to say the wall is, or if I were to say the wall is white, that would not be that would be synthetic, because I'd be taking it wouldn't be implied, and that white would not be implied in the definition of wall. Now, my question would be, and this is something I do not know. I know that Quine addressed this, but I'm a neophyte when it comes to this. My question would be, how does this apply to mathematics? In particular, maybe the debate between the Platonists and the nominalists in terms of, let's say, the number 2. One side might say that to say 1 + 1 = 2 is really a meaningless statement, because there is no 2 outside of the relationships that define it. There's no real number 2, it's 1 + 1, and that's the definition of 2 as it is a social definition, and therefore anything about mathematics would in a sense be analytic. Perhaps, this is the way I would think of it. Whereas for a Platonist, perhaps there is a 2-ness to the number 2 that's an inherent quality, and therefore would the Platonists suggest that there is an analytic and synthetic distinction in mathematics? I don't know the answer to this. This is a query to the mathematical philosophers in the audience. I'd like more information on this, personally. So I don't know everything, don't claim to. I'm just a YouTuber. I appreciate your time. Thank you very much.